Our next speaker brings together two complementary perspectives on quantum computing. The first one is solution architect. He is involved in practical integration of technologies in real-world systems and infrastructure that fits team needs. The second one is a theoretical physicist and a quantum chemist with a strong focus on quantum computing and quantum physics. And so they are here today to talk about quantum computing, more importantly, where we stand, what actually works, and what comes next. Please welcome Florent Houbart and Lennart Gundelach.
All right, so thank you very much and good morning, and thank you for being brave and choosing the English talk this morning. I will do my best to speak slowly despite the nerves. So I think many of you will have read some headlines over the last couple of months or years about quantum computing. And I think it's fair to say that the hype is real. It has been here for a couple of years now, and it is intensifying. And we have seen different headlines like billion-dollar investments by Qatar, IBM, Google, and other key technology sector players investing huge amounts of money in this technology. We see Microsoft, Google, IBM bringing out new generations of quantum computing hardware and announcing that it's a paradigm shift and that they're this close to making the final breakthroughs in this technology. And we also see slightly more scary, but often nonsensical headlines about how quantum computers and Chinese researchers are about to break all of our encryption algorithms, and all of our WhatsApp messages that we send are going to be read by the Chinese government in the next 6 months. And if you've been smart or lucky, you've maybe even invested some money in some stocks in quantum computing, like in the D-Wave stock, and over the last couple of years, you would have made a lot of money doing that. So overall, the landscape of quantum computing has evolved quite a bit over the last 50, 60 years, and today we have a huge ecosystem of companies, research institutions, and governmental players involved in this landscape. Everything from hardware providers, foundational research, from software offering integration partners, and those companies that are starting to explore real-world applications of quantum computing. So the message is, this is not one or two industry leaders focusing on it. It is already a pretty mature ecosystem of companies around the world collaborating on bringing this technology into existence. But let's take a step back and ask ourselves, why should we even care about quantum computing? And what makes it interesting? And why is everybody throwing money at this technology at the moment, in a similar way that we've been throwing money at AI as a technology over the last couple of years? And the key question is, what can we do with a quantum computer that makes it special? And the first thing is maybe kind of obvious, but actually very powerful, and it's the main historic application of quantum computing, and that is the idea that we can simulate quantum mechanical systems and problems, like in quantum chemistry or quantum physics, very well natively on a quantum computer. And it's actually very difficult to do that on a classical computer because quantum mechanical has lots of probabilities, lots of possibilities, and the problem spaces are so big, it's not very viable. So this is fascinating for research, but also for some industry applications. The second reason why we care about quantum computing is that quantum computers are, in theory, very good at solving combinatorial problems and also so-called very hard math problems, which is a big class of known mathematical problems, like traveling salesmen, factoring integers, etc., that are useful in a variety of domains. And one classic example of this is factorizing integers, which is a part of many encryption schemes that are generally used, for example, in web communication. And we can theoretically write algorithms on a quantum computer that allow us to solve these much more efficiently. And the final use case for quantum computing or quantum technology in general is secure communication, which is where we actually use the unique properties of quantum systems to communicate using them and to secure our communication via those special quantum properties. And if we look at industry, there's a variety of different industries that are starting to explore use cases sort of in a research R&D environment. We have healthcare that simulate drug molecules at a quantum level using quantum computers to do that natively. We have energy companies that have lots of minimization and optimization problems like energy forecast, grid usage optimization. We have logistics providers which have traditional traveling salesman problem and other combinatorial problems that they want to solve as efficiently, as quickly as possible, with huge potential scaling effects if they just increase their efficiency by 0.5%. And the same essentially in banking, where they have complex data structures, where they want to enhance speed and prediction for accurate pricing. And finally, we actually have one use case, at least that we could find and know of, that is already in production today, which is in retail, and it's again an optimization use case that Florent will tell you more about later, which is about auto-scheduling in retail and delivery. But where are we right now? What is this technology? How good is it today, and what can we achieve with it right now? So before we dive into that, let's remind ourselves quickly of what is quantum computing, what makes it special, and what makes it cool as well. The only difference really is that instead of working with bits, which you are hopefully all familiar, we work with qubits, and they're a little bit special. Instead of being 1 or 0, on and off, they exist in a state of superposition, in which they are both at the same time 1 and 0, on and off. And in reality, they are some sort of probabilistic mixture of these two states. And when we make a measurement of our system, let's say 1 qubit, it collapses based on some probability of its current state into either 1 or 0. And the reason that that is exciting, because it allows us to simultaneously explore many potential solutions to our problem at the same time, and then ideally collapse, make a measurement onto the minimal, most optimal solution of our system. The second property that is special about quantum mechanics in general, and which is a little bit spooky, is this idea of entanglement. We can connect one qubit with another qubit. We can then even decide to move them to the opposite side of the universe, and if I tickle one of them, the other one will laugh. And this is a property that is non-local, which is inherently a bit spooky. That means it does not require things to be physically connected in space to interact. This is the basis for all quantum communication technologies. And it is also not really causal sometimes. So it allows for some cool trickery around information transfer. Now, we saw some industry use cases and some potential examples, but all of them rely on the same premise, that there is a bunch of very hard math problems, and that we want to solve them on a classical computer. As we increase the size of our problems, we add one more stop in our retail route planning, the system size grows exponentially. And using a classical computer, even if it keeps scaling in size, we will take billions of years to solve these mathematical problems, which is kind of impractical, and that's the foundation of much of cybersecurity and encryption today. With a quantum computer, using this concept of superposition, we can, however, formulate algorithms that will scale not exponentially, but maybe linear with problem size. And suddenly we have the ability to solve a much larger version of these very useful math problems. And to give you an example, let's look at some numbers and factorizing these integers. For a 64-bit integer, it's no point using a quantum computer. We can factorize that on a classical system with an algorithm in milliseconds. But already at 192 bits, or a 256-bit integer, we see that it takes way too long to be practical, even on the largest possible imaginable supercomputer using classical computing hardware. So that's really the core value proposition of all quantum computing technologies. Now, when we look at the progress and the ability of quantum computing today, we distinguish kind of 4 stages of development. And for the last 50, 60 years, we've been stuck in the bottom left corner with research and lab stage. It's cool, it's interesting, but it's not a business use case, and it's not really that new or crazy. But we've managed to show quantum supremacy in a number of systems where we're able to solve a problem that is impossible to solve with classical computer hardware. And an example of that is simulating quantum mechanical systems natively on a quantum computer. But this is very rarely useful for industry application or for the IT sector. Then in the bottom right corner, we have the idea of quantum advantage. This is where we try to solve a problem we can already solve, just we solve it faster or cheaper or better. And this is really the area where companies are starting to explore their use cases of getting some money out of this new technology and becoming just a little bit better by moving from classical to quantum or quantum classical hybrid solutions. But what we're really after and what is motivating the billion-dollar investments into this technology is quantum utility, when we can solve new problems that we cannot solve right now, but that are also useful for industry, research, or business applications. And that's really the target and the goal that everybody is aiming for. Now, what is the challenge in getting there? Why is this so difficult? To be useful and to do this kind of world-changing work on a quantum computer, we would ideally want it to have around 100 logical qubits. Now, that's really not that much, right? If we look back at the 1970s, a processor back then had 500,000 bits. So, doesn't seem too challenging. And today, we do have quantum computing systems that have more than 1,000 qubits in the system. But the distinction there is that those are physical qubits, and they're not logical ones. A logical qubit is one which I can really use fully for gates, for operations, for logical operations. And the problem there, and the limiting factor that we have today, is noise and error rates. Quantum mechanical systems are, by their very nature, extremely unstable. And if they interact with the outside world, if it's noisy, if there's heat, if there's vibrations, they decohere. They collapse into one of the two states, for example, 0 and 1. They lose all their magical quantum properties, and they are of no value to us. So it's very challenging to build these resilient, coherent quantum systems with low error rates. So if we look at those 1,000 physical qubits, they have a too high error rate, and most of them actually cannot be used for computation, but have to be used as error correction qubits. Just like in a classical computer today, we have lots of bits designated for error correction and checking checksums, etc. So the state of the art today is that the top-of-the-line hardware that we have does have thousands or hundreds of qubits physically built, but really no logical ones. IBM Condor system, 1,200 qubits, but 0 qubits that can be fully used for logical operations. And Google Willow system, 1 logical qubit. And we need about 100 to get really useful. But the industry is quite optimistic. To be fair, they've been optimistic since the 1950s. But they say that they will reach useful quantum computing, so this idea of new problem and business value, in the next 5 years, by 2030 or so. So briefly, before we dive into some specific case studies and some examples, let's look at the 3 types of hardware that we have access to in quantum computing. We have gate-based quantum computers. This is analogous to your classical computing system. You teach it logical operations like AND, OR, XOR, and it's essentially universal, and you could play Quake on it. Now, this is by far the hardest computer to build because we need these coherent logical qubits. There's also an easier version to build, which is much more applicable right now to real-world problems, which are analog quantum computers. And instead of being general purpose and programmable, they physically represent only one specific problem in their quantum state, and only that specific problem can be solved on them. And we'll hear more about that in a minute. And the final option is to combine classical computing with quantum computing elements. Essentially, you solve the simple and fast part that doesn't scale so badly with a classical computer, so you free up your quantum system to look at those parts of the problems that have terrible scaling if we attack them with a classical approach. And finally, it's early days still, and we have lots of different hardware competing as to how we should actually construct a quantum computer. We can use superconducting qubits, we can use trapped ions, we can use lasers, so photons, topological systems, and there's more and more ideas coming out of research as to how we can build a scalable, coherent quantum computer that we're able to deliver that usefulness that the industry leaders are predicting. So yeah, I'd like to hand over now to Florent to tell us a bit more about how those quantum annealers actually work in practice.
Okay, thank you, Lennart. So if you get the point, we have gate-based computers that are not readily available now, so we won't get into detail of them now. Maybe in 5 or 10 years, speech will be different. We will get a look at what we have with analog system. We'll first deal with what we call quantum annealing system. This kind of system uses a quantum properties called quantum tunneling that is very useful to find the minimum optimal of a mathematical function. So if you have a problem that you can modelize in this kind of equation, this kind of computer are a good fit to solve to find the optimal minimum of this function. The computer does that and only that. That's what it makes it easy to scale. If you look at D-Wave computers, they are quantum annealers, and when IBM has 100 qubits, 200 qubits, D-Wave already have 5,000 qubits. But those qubits cannot be used for gate-based computing, just to solve this kind of equation. But because it is far more easy, it's less tolerant to noise. So we can find today's applications of this kind of systems. 5,000 qubits seems to be big compared to the 200 qubits of gate-based computers. It's small if you want to deal with real use case. 5,000 qubits is not enough. So we will deal with hybrid computing, where we will take big problems, cut it in small chunks, and send every chunk on the quantum computers. And we will have the same kind of thing you have with GPU. You take a big problem, you make small problems with this big problem, you solve the small problem independently, and then the classical computing takes all the solutions and builds the solutions of the big problems. This is exactly what does D-Wave. And we have one use case in production, the one Lennart was saying at the beginning of the presentation. Don't know if you know Canada. Patson Foods Group is the biggest retailer in Canada. They have more than 300 retail locations in 13 different banners. So they have a lot of different bargaining agreements, and their biggest challenge is to find how to choose which person will work at which time in the stores, and to allocate all of the resources to make the store works, but at the cheapest price. It takes them a lot of time. Since see the figures on the screen, it is the time spent by week and by stores. You multiply it by 300 stores. It's a lot of time, not lost, but it's a lot of time. They have the same kind of problem with e-commerce. When a customer orders some goods and you have to deliver it, which stores will deliver, which drivers will drive to the customers, and you have to allocate the drivers, the stores, to the delivery. And it's exactly the same problem, and they also spend a lot of time, 90 hours per week, to find the optimal solutions to deliver the goods and to minimize the cost. Okay, the costs are minimal, but they lost a lot of money building this kind of plannings. So what does D-Wave? They address this problem. They try to put it in the equations we solved before and generate plannings with the quantum computers. They come up with this kind of plannings, regular planning on time slot, who will work in each time slot, and it makes the retailer gain a lot of time, so they save money with this kind of solution. But more than the money, they can add in the equations the preference of the workers. The agreement says the worker would have to work 7 hours a day, for example, but this guy have this child to get to the school, the other one want to leave earlier for some reasons. And they can enter these preferences into the system, and it fits well with the equations. So even if they earn money by making the planning quicker, they also make their employee happier because they can satisfy their willings. So okay, it's what D-Wave do in Canada. If you want to do it now in your company, what can you do? We will try to make it live and show you what you can do, what you need to do if you want to take your hands on the quantum computers. So we tried last year in SII to build what D-Wave made with Patson Food Group, and which shows a problem that is incredibly similar. Imagine you have a lot of people that need to go to rooms, like the DevFest, for example. You have invited a lot of people, and you have to find hotels for every of your guests. Some guests have some preferences, and some rooms have some features. Not every guest can go on every room. If you have disabilities, maybe you cannot get on the room at the first floor. If you have children, maybe you need the big rooms, and so on. You don't have enough room for everybody, so you need to find the optimal accommodations that will accommodate the most of people, but also optimize the value of the people you will accommodate. So how to deal with that? Easy. If you like maths, just have to write some equation. And it's what you do when you program quantum annealers. You don't write code like writing Python or Java or so on. You write mathematical equations. And the code you write is just to send these equations to the QPU, the quantum processing unit. So I won't go into this particular equation, but just to show you how easy it is. If you fit the problem in this equation, these 3 equations are how you handle the problem of resource assignment. You write these 3 equations, you write a bit of Python code, it's less than one page of code, to send these equations to the QPU. And it was on D-Wave system. D-Wave solved this problem and give you an answer pretty quickly. Last year it was fine. We have free access to D-Wave system. We can run demo. We cannot show you today because the D-Wave changed their pricings, and we need to spend nearly $100,000 for a developer seat just to run a demo. My boss wasn't agree, so we don't do it. But it's really interesting because it shows that D-Wave changed its pricing model because they are entering the business and they think now they make money with it. So they sell it to customers. I call them to get a demo anywhere and they say me, if you have some customers, send them to us and we will build something with us. They are really entering this business phase and they are building the system to go to production. So let's D-Wave apart and we'll try to find something else. Bit less mathematics, but fair enough. Do you know this kind of problem? Math set, you have some graph, some nodes connected with edge, and you need to find the maximum number of nodes without any connection with each other. So you have here 6 different solutions. The solutions at the middle here are the optimal one. You have four nodes. If you add 5 nodes, you will have 2 nodes connected, so it's not a good solution. You have here the mathematical formulation of the problem. I won't go into it, but what is interesting in how this problem transformed to real use case, so the other side, how the real use case can map to this problem. You have 2 examples of use cases that you can see today. First one is what you can see you have in telecom business when you have to upgrade 4G antenna to 5G antenna, for example. Your 5G antenna are very sensible to interference, so you cannot have 2 antennas near each other which are both 5G. 4G is less sensible, so you have a lot of antennas everywhere in France, but they are too near each other, so you cannot upgrade both of them to 5G. So if you want to upgrade your existing set of antennas, you have to find the maximum independent set of your existing 4G to optimize, to minimize the number of new antennas you have to build. And the second use case is more fun. Let's imagine you want to make a big football team. You don't want to have in your team 2 people who hate each other and can't work together. So how you can find the maximum number of people that can work together? You just make edge between people that won't fit to each other, and you want to find the maximum independent set of this graph of people. So it's 2 real use cases you can find in production. We will try to solve this problem with another kind of analog quantum computers. So it's Aquila. Quera is the provider. Aquila is the model of QPU. The idea of Quera is completely different from D-Wave. They don't solve mathematical equations. They work directly at the physical level of the qubits. When you write a program to run in Aquila, you already play with atoms. You put atoms on a grid and use what is called the Rydberg effect to have a solution to our problem. So Rydberg effect says that if 2 atoms are close to each other, not both of them can have a high energy level. The first ones that we get in a high energy level will block the other one, and it will stay at the low energy level. And thanks to what Lennart said at the beginning, the superpositions, our system will go into every possible solutions of the system, but with this constraints of the Rydberg effect. So we see that it maps easily with the problem we are trying to solve. So we will now make it. So I switch my screen and go back to my laptop, just to show you how we can make it. So we'll start just with a small graph. So I generated a graph on a 5x5 matrix. I have some nodes, and I want to find the optimal minimum, the maximum independent set of this graph. We'll first try to solve it brute force. So my laptop is going through all the different solutions. It takes less than 1 second. Computing is completely useless here. And it finds a solution with 7 nodes. The red nodes here. You cannot add 8 nodes because I go through all the solutions, and this is the best one. So let's make the same one now, not with 5 nodes, but with not 5, but bigger screen grid. So it's bigger grid, and we want exactly the same solution. So let's let the computer compute. It's still computing all the different solutions and trying to find the optimal one by going into all different possibilities. While it's working, I will just show you what we have at AWS. We use a service called AWS Brackets, which is AWS Quantum Services. And you can, thanks to this service, send your quantum task to different quantum systems. So this is real systems that you can use in production. You have a lot of gate-based computer. You can see the number of qubits is not very high. And you have the one that is interesting us today, Quera Aquila, with 10 times more qubits. It's not because the computer is most powerful, it's just because it is analog computing, so it's easier to scale. You don't do the same thing with Quera than you do with IonQ. IonQ is gate-based computers. Let's just look at the price. It's pretty small. So if you run a task, you have to pay 30 cents by task you run to the QPU, and then one cent per shot. The idea of the shot is that because the computer is very noisy, you send a computation, it won't give at the first time the best solution because of the noise. So you want to send it 10 times, 100 times, 1,000 times, and take the optimal one or the average of the solution depending on your problem. So if you take 100 shots, for example, you will pay 30 cents and $1, so a bit more than $1 for 30 cents, still about affordable. So let's go back to our solution. The computer has not yet finished. I will kill it because, as Lennart said before, we will have to wait until the end of the universe so that we find the solution. So let's send it to the quantum processor. So this script is using exactly the same graph than before, but you won't go into all the solutions. You will anchor it in Quera Aquila. So you have here in the right for you every red dot. It's not the graph, it is the location of an atom on the QPU. And the blue lines are the Rydberg effect. So I just encoded the graph as is on the QPU by placing all the atoms where I want them to be. And what you have on the left is how we program the laser beams that manage the energy level of the system. So we won't go into the detail, but the idea is that we put the atoms where we want them to be. We increase the energy level of the system. Because of the superposition, the system will go into all different possible solutions. And when the system decreases in energy, on the last phase of the algorithm, the atoms will collapse into the best solutions. This is the one we are looking for. Now, while the algorithm is running, I will just run another one to solve it with a classical computer. We'll go by it later, but just because it takes some time. So I will go now to the quantum task. I see here all the tasks I sent. So we make a lot of tries this morning. One is here. It's still running. It's not so long. OK, it's completed. And we can show here the parameter of the job. I asked for 70 shots. It's not so much, just to have $1 per job. And when it's finished, the solution is sent to S3 buckets. S3 buckets. I will just download it and see what we have. This one is still running. Let's see, 5. So this is what the quantum computer finds. As there is 70 shots, every shot gives a different solution. Statically, the most often solution is 70 nodes. It's not the best one. The best one it finds is 76 nodes. So it's right on here. So because we want the optimal solutions, we will take the last one. If we had a problem where we want the most often occurring solutions, we will probably take this one. So we have a solution here with 76 nodes. It's better than waiting the end of the universe, and it cost me little more than $1. Okay, this one is finished. So I make the same thing with an heuristic algorithm. So it's classical computing. It's not the optimal solution, but it tries to find with the simple algorithm, try to find an optimal solution. And this script takes 2 or 3 minutes, and it finds a solution with 86 nodes. Too bad, it's better than my quantum algorithm. So what we wanted to show you here is not that quantum will change your life now, because it's cheaper to make it with an heuristic algorithm, and it's working, and it's better. But the idea is that it's very easy. I just write 3 Python files. It takes me one day to write it. You have some computer readily available. It's more complicated to go into gate-based computer because you have to get into all the trouble of mathematics behind. But this kind of solution is very easy to use. They are not. It does not give the best solution. In the demo here, I use all the default parameters of the QPU. If we really want to fine-tune the model with a problem, we can get a better solution. And we just solve a small problem. If the small problem gets bigger and bigger, the quantum processor can get an advantage with classical computing. So the moral of this story is that you have some quantum computing available. They are ready to use. You can use it. It's easy to use them. Will it change your life now? I'm not sure. But if you hear what IBM say or other players in the market, in 5 years, it will change your life. So is it time to get into it? Maybe.
All right, so we've seen that any of you can log on to AWS, set up an account, and you can start implementing Shor's algorithm for integer factorization today, and then tomorrow you will hack everybody. So what is preventing us from doing that? Of course, the hardware limitations that we've seen, but there's been a lot of headlines last year and again this year about, oh, we're almost there, and maybe all our data has already been hacked. So let's have a closer look at cryptography and the idea of post-quantum cryptography, because this is something that might be actionable for you, for the software products that you develop, for your companies, or for your personal hobbies that you have as well. So a quick reminder, what is cryptography? It's just, I really like the definition on the left, it's the art of writing and solving code. That's it, nothing more to it. So how do we traditionally know that a cryptographic algorithm is safe? Do we just take a guess? Do we let a bunch of people try to hack it? Essentially, we start by taking some cryptographic algorithm, and there are many, many. Some famous ones are RSA encryption, Diffie-Hellman, etc. And what we try to do is we map them to a known hard mathematical problem. So we go out searching for some math problem that's been well studied, and ideally a math problem where we have a proof that it cannot be solved, or it can only be solved with terrible scaling on a classical computer. So with an example of RSA, we map it to factoring integers. And so, because we have proof somewhere from some mathematician that showed that this math problem cannot be solved, we reverse engineer our cryptographic algorithm and we say we trust it, it will be fine. So what's the problem with quantum computing when it comes to this? Let's take RSA as an example. We mapped it to the known hard problem of factoring integers, and that will be difficult to do on a classical computer. But now comes the potential threat of quantum computing. We've seen, okay, we can use Shor's algorithm, which has been known since the 60s essentially, and if we combine that with a powerful enough quantum computer, let's say with 100 logical qubits that we allegedly will have by 2030, then we no longer have this terrible scaling, but we can decrypt our keys maybe in a day or two. All right, so do we need to start panicking? Is this a problem? Are we all screwed? And the reality is that today, the threat is literally 0%. And anybody who tells you something else is lying to you. Or they know something that we don't know, but I don't know. There's currently no hardware available, at least in the public realm. Maybe some military has something hidden away in a basement, but even that I doubt, that has remotely enough computational power to decrypt anything that is currently a security standard. And anything that is being promoted in the news is immediately debunked by scientists who work in that domain. Now, that doesn't mean you're not affected, because all of you and me and Florent, we will all be affected by this sooner or later, either in our work or our personal lives. And the reason for it is that we all use, in the software that we use, in the technology that we use, in cryptographic algorithms that are, in principle, susceptible to this type of attack. So the important question is then, when is it time to panic? When is it time to get ready? And frankly, nobody can tell you, because we know the theory that's been done since the 1950s and 60s. We have the algorithms that have been consistently improving, at least theoretically, over the last 50 years. And the hardware is improving incrementally year over year. And, any day there could be that paradigm-shifting technological discovery, a new physical system that we can encode qubits into that is more stable, that has longer coherence times. But the one risk that exists today already, and this is a strategy that researchers have found is being exploited, is the idea that we collect now and we decrypt later. So there are parties out there that are going to collect all the different information and messages that they can gather from networks that are currently encrypted and uncrackable. But then in 5 or 10 years, they will go back, they'll decrypt it, and try to reverse engineer an attack angle out of that information. Okay, so let's look in detail at some of these quantum attacks that we've seen in the news. So the state of the art for factorizing integers right now is this number down there. It's like 8 million something, something, something. This is the biggest that has been achieved on an actual quantum computing system that has been verified by scientists. So it looks kind of impressive, but then this is a 2048-bit RSA key. And even with quantum computer, our scaling is not perfect, and so we are far, far away from decrypting that with today's hardware, just to make that very clear. Now, we know that this might become a problem or will become a problem in the next couple of years, so what can we do, both as organization and as individuals, to prepare for this upcoming problem, right? Because we know that it will affect all of us. And we have two strategies that we can employ. The first strategy is what we're going to talk about today, which is post-quantum cryptography, finding cryptographic methods that are immune, or resilient at least, to quantum computing algorithms. And the other approach, which is cooler but kind of impractical as of today, is quantum-based communication. This is where, if you remember back, we used those spooky idea of entanglement and superposition to send keys and encryption information from one place to another using quantum mechanical qubits, like photons, for example. And this is being done. There's some banks who are playing around with this and using this to secure their key exchange systems, actually. But it's very impractical at scale, because right now we don't have the physical engineering technology to really do this for everybody. So let's look at post-quantum cryptography instead. All right, remember, we need an algorithm, we map it to a hard math problem, and we show that it's impossible. And so the only thing we need to do, very easy, is we have to find new math problems that are really hard, not just for a classical computer, but that are also, by definition, really, really hard for a quantum computer and for the type of algorithms we can develop on a quantum computer. Luckily, we have lots of crazy mathematicians running around somewhere, and they have found lots of these math problems. So all we have to do is take one of them, we reverse engineer a cryptographic standard out of it, and we claim that it is safe. Seems pretty straightforward. Now, there's been a couple of screw-ups along the way, like, for example, developing a cryptographic algorithm that is safe against quantum attacks, but vulnerable against a classical attack. So that has happened repeatedly over the last couple of years. But if we look at the current state of the art, we have the National Institute of Standards and Technology, NIST, which has published its first highly official, super vetted and validated standard for post-quantum encryption algorithms. And we have a choice of, I think, 2 algorithms for public key encryption, and we have some more algorithms for digital signatures. Crystal's Kyber, I think, is Yu-Gi-Oh! Inspired, and Crystal's Dilithium. And these algorithms have been published. They're available, they have SDKs, they can be implemented into your technology today, in principle. And the target has been set, for example, by the US government, that all critical infrastructure must be secured via these new standard algorithms by latest 2035. But I suspect that given the public communication of IBM, etc., that the timeline is more like 2030, that this target will shift closer into the present rather than into the future. And there are a number of other similar alliances, essentially in the cloud as well. Lots of the big hyperscalers in the cloud are collaborating together to also implement these new encryption standards into their cloud platforms and the communication services that they provide. And some standouts are OpenSSH, for example, added a new cryptographic algorithm, PQC, that is in principle quantum resilient, and other providers like Microsoft, Google, IBM have been implementing these tools into their environment. All right, so let's briefly summarize what we learned. Quantum technology is cool, kind of spooky, and we know for sure that it will someday be useful. But we don't know when, because it's very difficult to predict the advancements in hardware and engineering needed to make it happen. It's a lot like taking ourselves 3, 4, 5 years back and asking ourselves, what will AI look like in 5 years? And some people might have said useless, some people might have predicted where we are today, and some people might have been praising we will have AGI and we will all be eradicated already. And it's kind of the same with quantum computing. And I think the key takeaway that I hope you take from this talk is that it's not that complicated. Anybody can get into it, get it running, play around with the technology, have a basic understanding of it, and be aware that what you build, whether it be personally or for your companies, will someday be affected. And the hurdle to prevent that risk and to inform your organization to assess that risk and just to prepare a plan, to have that feature, to have that epic in your backlog that says, hey, let's see if we can do a proof of concept implementation of one of these post-cryptographic algorithms. That's already the necessary step and will be a good safeguard for yourselves. I'm Lennart Gundelach. I'm head of data and AI at SII Group in Germany.
And I'm Florent Houbart, solution architect at SII France.
So thank you very much for your attention, and we'd be happy to answer some questions.